Today we are explaining the paper self-improving pre-training using post-trained models to pre-train better models.
What is the big idea of this paper?
The paper argues that safety, factuality, generation quality, and reasoning should not be bolted on only at the very end. Instead, it moves those behaviors earlier into pre-training and mid-training, so the base model learns them as part of its core behavior.
What was missing in earlier training pipelines?
Earlier pipelines usually do next step on pre-training first and only add instruction following, safety, or reasoning later. The paper says that is too late, because the model has already absorbed low-quality patterns. And filtering bad documents does not teach the model how to recover when a prefix is unsafe or misleading.
So how does self-improving pre-training change the setup?
The model no longer predicts just the next token. It reads a prefix and must generate the next chunk, which the paper calls a suffix. A strong post-trained teacher helps into roles. It can rewrite the suffix into a better target, and it can judge the current policy's rollouts against the original and rewritten suffixes.
Why do they need both the rewriter and the judge?
The rewriter gives the policy a cleaner target when the source suffix is unsafe or weak, while the judge decides which candidate is best at each step. That matters because early in training the policy's own rollouts are poor, so supervision comes mostly from the original suffix or the rewrite. Later, the policy improves enough that its own rollouts start winning.
What does the first equation tell us about the rewriter?
Equation 1 handles the easy case when the suffix is already safe, so the reward is 1 only if the rewritten suffix exactly matches the original safe suffix. The paper uses that to stop the rewriter from changing good text just for the sake of changing it.
And what changes in the unsafe case?
For unsafe suffixes, exact copying would be wrong. So the second equation scores a rewrite by averaging the judgments. Is the rewritten suffix safer? And is it still a good continuation of the prefix? That keeps the method from replacing unsafe text with something bland.
Does the judge actually become reliable enough to doctor training?
This result says yes. On the validation curves, safety reward climbs from roughly chance to above 0.9 very quickly, flattening near step 100. Quality improves more slowly, which fits the author's claim that early models favor endings that merely feel complete instead of endings that really match the context.
What does the rewriter learn on its own validation curves?
The rewriter has to solve two opposite jobs. It should rewrite unsafe suffixes. The validation curves show progress on both. Unsafe rewrites move up from chance level safety performance, while exact match reward on safe suffixes starts near 0.1 and keeps rising throughout training.
How much of the safe text survives after rewriting?
This plot makes the behavior clearer. For safe suffixes, token overlap climbs towards 0.98, so the model mostly copies text that is already fine. For unsafe suffixes, overlap stays around 0.63, which means the model is willing to make real edits when it needs to steer the continuation in a safer direction.
Do those training signals translate into better model behavior on full evaluations?
Yes. In continued pre-training, the quality-focused version reaches an 0.3 win rate on generation quality, compared with 49.0 for the pre-training baseline, and coherence rises from 49.4 to 87.9. The factuality-focused version lifts the factuality average from 40.3 to 57.6, and the safety-focused version raises average safety from 76.9 to 91.1, while still winning 77.7% of comparisons on unsafe prefixage.
The paper also has a second half about reasoning. What changes there?
The second half applies the same philosophy to reasoning. Instead of waiting for final post-training, the authors augment pre-training data with explicit thought traces, then run a two-step mid-training phase. Supervised learning on thought-augmented data first, followed by reinforcement learning that teaches the model how much thinking to do before predicting the next sequence.
How much does that help before the final post-training stage?
Quite a lot. On Llama 380, training on thought-augmented data raises it to 0.1 to 49, and adding ARL mid-training raises it again to 0.1896. The paper highlights that this is about a 9 times improvement over the base model while using less data than simply scaling raw data. Mid-training.
And after the final ARL post-training, what is the payoff?
The payoff is that post-training becomes much more effective when the model already learned useful reasoning patterns during mid-training. Direct ARL post-training on the base model reaches an average of 0.1197. Thought-augmented supervised mid-training plus post-training reaches 0.3480. And adding 5,000 ARL mid-training steps pushes that to 0.3785 with 8.7 billion tokens, while the largest setting reaches 0.3837.
So what is the clearest takeaway from the whole paper?
The clearest takeaway is that stronger training signals should arrive earlier. A post-trained teacher can improve pre-training by rewriting weak targets and judging better continuations. And thought augmented mid-training makes later reasoning post-training much stronger. In both halves of the paper, the same lesson holds. If you wait until the last stage, you leave too much value on the table.
That makes the paper's logic much clearer. The training recipe is really about shifting quality control and reasoning into the stages where the model is still forming its habits.
That wraps up this paper walkthrough.